Let's work out an example of series. Suppose that we want to find if the following series converges or diverges. The sum from n equals 2 to infinity of 3 times 4 to the n minus 7 times minus 2 to the n minus 1 divided by 5 to the n. So in here, what we need to do is to find out if this series is going to give us a number or not. If the series gives us a number, it is very convenient to find what that number is. The procedure for working with this expression is very similar to the one with integrals. We can split this expression into pieces. By this, what I mean is that we can break this fraction into two fractions. The first one being 3 times 4 to the n divided by 5 to the n, and the second one is 7 times negative 2 to the n minus 1 times 5 to the n. Now in here, we can rewrite this expression as two sums. The first one is from n equals 2 to infinity of 3 times, we can actually write this down as 4 over 5 to the power n. And then the second one is n equals 2 to infinity, 7 minus 2 to the power n minus 1 divided by 5 to the power of n. Notice that in this case, we cannot do the same trick as with the first one because the two exponents are different. In the first case, both exponents were the same. We had 5 to the power n and 4 to the power n. In this case, we have an offset with these two indices. So what we can do is we can rewrite these powers so we can have the same power for both the numerator and the denominator. So the first one stays the same, and the second one we can actually factor an extra 5 to write down as 7 over 5 times negative 2 to the power n minus 1 and 5 to the n minus 1. So in this case, the trick was noticing that the denominator could be written as 5 times 5 to the n minus 1, and that will give us the original 5 to the n. Now, what we have is that this expression is convenient for us to write it down as a single one. That means that this becomes sum n equals 2 to infinity, 3, 4 fifths to the power n, minus n equals 2 to infinity, 7 over 5, and then we have negative 2 over 5 to the power n minus 1. In this case, notice that we have two geometric series. We have that this is of the form a r to the power n, and this is of the same form. We have something of the shape a to the ratio power n minus 1 in this case. So we have that these two are geometric series, which means that we can actually apply the result for geometric series that if the ratio is smaller than 1, we have that the series converge. So for both of these, we have that in this case r equals 4 over 5, which is smaller than 1 in absolute value. And for this case, we have that r equals negative 2 over 5, which is smaller than 1 in absolute value. That means that for both of these, we have that the series converge. So that means that both of these expressions exist and give me a number, which means that we can actually compute this number. So first we have that this series converge, this converges, and then we can actually find what this number is. So this means we can keep simplifying this expression as 3 times the sum n equals 2 to infinity of 4 over 5 to the power n minus 7 over 5 n equals 2 to infinity of negative 2 over 5 to the power n minus 1. Now we have that any geometric series can be computed using the following expression. The sum from n equals 1 to infinity, from n equals 0 to infinity of r to the n, that is equal to 1 over 1 minus r to the n, provided that r is smaller than 1 in absolute value. So the important thing in here to notice is that the index at which we starting is pretty important. This formula is only valid only in the case when we're starting at n equals 0. So in these two cases, we are actually starting from n equals 2, which means that we cannot directly apply this formula over here. But nonetheless, we can work it out in order to make it work. The important thing in here is to notice that whenever n equals 0 in this expression that we have, the first term, the corresponding term, should be equal to 1. This is my guiding line in here. In other words, if I can make any arrangements to these two expressions that I have in here such that the first term is actually a 1, that will give me a way to actually work out with this expression that we have over here. In other words, what we can do is the following trick. We can have a common factor so that it can actually start at 1. In other words, notice that the first expression, we're starting from n equals 2, which will be this, then n equals 3, and so on. Likewise, with the second expression, we are starting from n equals 2, which will give me negative 2 over 5 to the 2 minus 1, plus negative 2 over 5 to the 3 minus 1, and so on. Notice how in the first expression, we're starting from 4 over 5 squared, which means that only for this expression, we can actually take a common factor of 4 over 5 squared, which will give me 3 times 4 over 5 squared, factor of 1 plus 4 over 5 plus 4 over 5 squared, and so on. Which means that if I do this common factor, I can actually start from this corresponding term equal to 1. In other words, if I take this common factor over here, I can actually apply the geometric series formula. Now for the second expression, notice that for this expression, we are actually starting from a power of 1 because our first exponent is 2 minus 1. In other words, what we could do in here is to take a common factor of 2 over 5. In other words, this could be negative 7 over 5 times negative 2 over 5 as a common factor of 1 plus minus 2 over 5 plus minus 2 over 5 squared, and so on. In other words, what I'm trying to do in here is to find what are the factors that I have to take in order to convert the original expression into a geometric series that I can work with. So this turns out to be 3 times 4 over 5 squared. Sum, let me use k now. K equals 0 to infinity of 4 over 5 to the k power. Minus 7 over 5 times negative 2 over 5. I can use a different letter in here. I can set m equals 0 to infinity of negative 2 over 5 to the power m. And this expression is the exact same expression as we had before. But now the difference is that I wrote it in such a way that the very first term of each of these is actually going to be 1, which enables me to use the geometric series formula. So I have that the first part is going to be 1 over 1 minus 4 over 5, using the geometric series formula, minus 7 over 5 times minus 2 over 5 times 1 over 1 minus negative 2 over 5. And this is the actual sum. This is the value of the sum. So if we simplify this a little bit, we will have 3 times 16 divided by 25, 1 over 5, minus plus 7 times 2 divided by 25, and this will become 1 over 1 plus 2 over 5. That will give us 7 over 5. If we keep simplifying this out, this will give us 3 times 16 divided by 25 times 5 plus 7 times 2 over 25 times 5 over 7. So this will cancel some things. We have that the 7's cancel, the 5 will cancel with one of these 5's over here, and also this 5 will cancel one of these 5's. So in the end, we end up with 3 times 16, that is 48, divided by 5, plus we will have 2 divided by 5. This gives us 5 divided by 5, which is equal to 10. That means that the original expression that we started here is convergent, and whenever we add it up, it gives me 10.